Okay, so today we're gonna learn about light cone. This is structure of light cone here. Okay, but we will slowly develop the ideas related to it. Okay, so we have learned till now, uh, of course, the master equations of this special theory of relativity. Let me increase this something. Yeah. So in special theory of relativity, we have Lorentz transformations that transforms transforms our coordinates from one inertial frame to another. Okay, you got it. And what are these Lorentz transformations are? And these are x prime. Let's start with the t prime. Okay, it's t prime gamma t minus v by c squared and x. Okay, these unprimed coordinates are of S frame, that is stationary, considered as stationary with respect to us, suppose. And this is by conventionally the prime coordinates are taken from the in the S prime frame that is considered conventionally as moving frame. Okay, so for x prime it is x minus vt. Okay, y prime is equals to y, z prime equals to z. Okay, in S prime frame the coordinates are described by these prime coordinates, and in S frame this event is described by, okay, these are the things. Further we can write this as in interval form. Okay, as del t prime equals del t prime, sorry, minus b c squared del x prime gamma del x minus b delta t. Means these are for 1D motion. It is for, okay, 1D motion of S prime frame. Okay, that is x direction. Okay, and more symmetrically we can similarly write it like this, uh, in the beta form. Okay, so we can simply write this again as, this is c here, delta t minus beta, okay, del x prime equals to gamma del x minus beta. This is, let me write it again, C delta t. We will see why are we writing these in this form, because it is easier to, because you see the time coordinate, we can make this time coordinate a length coordinate by multiplying it by c, and we will see, I mean we are seeing this, that the equations look more symmetrical now. Okay, so in previous class we have talked about, in previous class we talked about an invariant quantity, and it is most important invariant quantity in whole of STR, that is space-time interval. Okay, it is a infinitesimal distance, or say yes, magnitude, square of magnitude of infinitesimal uh, distance in space-time, four-dimensional space-time. Okay, we describe it by, denoted by del s squared. Okay, it is a square of the magnitude of the distance, infinitesimal distance. Not infinitesimal, it is general, but we can take it as ds square if we are considering the infinitesimal one. So just we take it like usual, del s. Okay, now we say that in previous class we talked about why it would be an invariant quantity, because it should be invariant, because we are due to the postulate, second postulate, we are considering the speed of light should be constant. So in all frames like o p by t, it should be o prime t in prime coordinates, it should be same. So this will imply like what it will be, yeah, x prime x square, when you consider the distance upon time, it should be same in prime coordinates. And when you will take the interval form, it will look like same equations. Okay, and when you make them equals to like, yeah, it is c, and when you make like, you will find that for light, of course, c squared t squared from these equations equals to x squared plus y squared plus z squared should be equals to minus, not c prime, c is constant in all frames, plus x squared plus y squared plus z squared, and these are all prime coordinates. Okay, so that's how, due to the second postulate, this interval should be invariant under the transformation equations. Let's see for example, let's see, let's check check. Okay, we'll quickly check it so we can discuss further on some other things. So suppose del s prime, this is this. Okay, so from the Lorentz transformations, okay, from LTs, you can check it that del t prime should be equals to gamma. Okay, let's take the this directly, these equations, the symmetric form. Okay, let's take this one. So from here you can directly see that c delta t prime is equals to gamma this. Okay, so you can directly write this c delta t. minus beta del x to the whole squared. Okay, this quantity, and with a, of course, with a minus sign here. And this one will be gamma squared del x minus b delta t to the whole squared, plus, again, this will be invariant already by these transformation equations because they are same, del y and del z. So now you can expand the both sides, but before that you can take the gamma squared common. So we will see that minus c squared delta t squared, okay, and minus beta squared del x squared, and this would be like minus, but due to this minus it will be plus c beta delta t and delta x, right? And now just expand this here, the second term. The second term, it will be del x squared plus b squared delta t squared, right? And of course minus 2, sorry, here it should be beta because we have taken the symmetric form, beta c. Okay, so again this will be c beta delta t and delta x. Okay, so this should, this is plus sign, plus of course this same thing. Now you can see the whole, this quantity cancelled out, and the remaining quantity is this, and from where we can take the common del t squared and del. So you can take common like del t squared first. So it will be v squared minus c squared, and when you take the del x squared common, you will see 1 minus beta squared is here. Okay, so this is, and again when you take common out the minus c squared from it, minus c squared delta t squared, we will get 1 minus c p squared upon c squared. Okay, 1 minus beta squared plus same. Okay, now you see this is again my same thing, 1 minus beta squared. Okay, see. So 1 minus beta squared can be taken out common, and this would be delta t squared plus delta squared plus this whole term, right? And you know already that this can be cancelled out because this was, since this was 1 minus b squared by c squared, we have defined a gamma like this. So this will imply that gamma squared will be equals to 1 minus v squared by c squared, which is also equals to 1 minus beta squared, where my beta is v by c. Okay, so you can see this will be cancelled out whole thing, and you will see that del x prime will be equals to now as this plus del x squared plus this. So this is equivalent to, this is equal to the interval in the stationary frame, that is S frame. So it is, of course, it is called as Lorentz invariant quantity, and it is very important quantity in all of relativity. Okay. Now let's talk about something called time dilation. Okay. Time dilation. Okay, let's talk about time dilation. So it assumes colloquiality, locality. Okay, to see the time dilation perfectly, you need to assume co-locality. Let's see how. Suppose there is a digital clock. Okay, kind of digital clock that blips every interval of time. That is delta t prime. Okay, in a moving frame. So what do we have? We have a moving frame where we have a moving frame. So this is z prime, x prime, and this is moving with some velocity. This is my s prime frame. Okay, so we have okay, this is some, suppose light blips here. Okay, or say you can say every delta t prime. Okay, in every, yes. So this is a digital clock, suppose, and why are we taking this? I will tell you. And this is a stationary frame. This is S frame. We take its coordinate like this. Okay. So with respect to S frame, the S prime frame is moving in the rightward positive x prime direction or positive x direction. Okay, with a velocity v. It is a constant velocity because we are taking inertial frames. No forces are acting on this S prime frame. And we are considering a digital clock because there should be, because we want to assume co-locality of these events. Event 1 is described like first blip of light, first blip of light, okay, event 1, and event 2 is described at second blip of time of light, okay, and it is taking some time, that is delta t prime in this prime coordinate. If we have assumed, like if we have taken the analog clock like this, but in this we are seeing that these two ticks are not and these two ticks are not co-local in analog one, analog clock, not co-local actually. But you can assume this digital clock, these two events are happening at same place. Co-local means same place, at same location. Okay, so these two events are co-local in S prime frame. That means in S prime frame, the difference between the location of these two events is 0. Okay, it is 0. Now you have Lorentz transformations in interval form, like again take the same thing. You can take C, symmetric form or any form. The things will not change. Okay, let's just take these coordinates only. Let's not take other coordinates because the motion is not. things. So let's give it as this. So you see, this is 0. Okay, so this implies delta. 0 implies that delta x is equals to v delta t. Okay, of course, this is the measurement taken in the S frame in the stationary frame. Of course, you can see that while the difference between the location of these two blips is like 0, means the two blips are co-local in this S prime frame. It will not be co-local in the S frame. It is easy to see because this whole frame with the digital clock is moving uh, with a long time. Okay, moving in the rightward direction. So uh, yeah, when you record the first blip in this frame, and then you record another blip in this frame, it will take some time. Okay, and in that time this whole frame will move rightwards. Okay, so it is simple to see that the location of these two blips in this S frame is not 0 because of the motion of S prime frame. Okay, do you understand this? Right. So it was simple to see. Now you just use space-time interval, invariance. Okay, that is s prime squared is equals to s squared. Okay, what was it? It was c squared del t prime squared plus del x prime plus del y prime equals to minus c squared del t squared plus del x prime del x y prime. This will be okay. So of course you can take this here. So you do this. Okay, these things will be cancelled out, and the remaining thing will be this. And use this equation first. Uh, Wait, yeah, okay. This will be 0, right? So yeah, yes, this use this equation here. So minus del t prime squared would be equals to this del t squared plus v squared del t squared, right? So you can just take it out common and see. Okay, you take this common, you will see, you will get this thing. Okay, and you get this as del t squared. And from this you can get like del t is equals to del t prime upon 1 minus v squared by c squared. Okay, this is the expression for time dilation. Okay, what did we assume? We assumed only two things, that speed of light is constant. Let me write it separately. Let's assume first constant speed of light to derive this. Okay, that is invariance of this thing. And second, two events are co-local moving frame. Okay, that is del x prime is equals to 0. So from these simple assumptions, okay, we reach to this conclusion of this time dilation. Okay, now this is called proper time interval. Okay, this is called proper time interval because the clocks are not moving in the moving frame. The clocks are at rest at in the moving frame. Okay, clocks clock is at rest in moving frame. So we consider this as a proper time interval. Okay. And but you will see in it is get the this proper time gets dilated gets dilated, okay, in stationary frame. Okay, this stationary frame is like with respect to uh, us, say yes, and yeah, as suppose we are the observer observing the event or say these events from this stationary frame. With respect to us, the S is at rest. Okay, so you can also write down this as improper time interval between events is equals to proper time interval divided by 1 by 1 minus v squared by c squared. Yeah. Now let's talk about length contraction. Similarly, length contraction in similar fashion can be derived as, okay, consider a rod, okay, a moving rod, length, uh, let's take it del x prime, okay, in its own frame, okay, and so we define it as proper length. We call it proper length, okay, because the length observed by the observer in this S prime frame will be, because the rod is also moving and in its own frame the length is considered will be proper, but we will see that in our frame what will happen to this length. So this is my S prime frame, S prime frame, and I have a rod here, suppose, okay, and it has some length, that is fine, or you can take its height also, it will not matter much. And this is my again, and this rod is moving with velocity v with, and S prime, in this S prime frame this rod is at rest because this whole stuff is moving with same velocity, and this is my S prime frame which is stationary, okay, with respect to its us or say any observer. For this observer, this whole thing is moving at speed v. Now just see quickly that what will happen? Here we will assume for the length of contraction, the thing is assume simultaneity. Okay, assume simultaneity. Length measured perfectly in S frame must measure the whole length simultaneously. Okay, consider first event 1. Okay, measurement of, like, suppose this is uh, the end of measurement, end part of rod. Okay, suppose this is A, this is B, this is the front part or this is the end part, and this is given to is measurement of front part of the rod. Okay, so in S frame, if we want to measure this, okay, if we want to measure this in frame S, then we must measure it simultaneously. Okay, simultaneously. It means these events. Measure these events simultaneously, which also means my del t should be 0. Okay, so we again take Lorentz transformations, that is del t prime is equals to gamma del t minus v by c squared del x, and del x prime is equals to del x minus v delta t. Of course, this will not be affected. You can take this as 0. Okay, there is no length in the y direction, and you can take this as some z naught. Okay, this is because the transformation equations do not affect this length in the z direction, or say the height will not be affected in any measurement. Okay, so you can take it or not take it, it's upon you. So, and now consider again the invariant. Consider, okay, again the space-time interval invariance. Okay, so this will imply that minus c squared delta t squared plus this equals to this. Okay, so this will be cancelled out, and this is z naught. This is also z naught. So this will also be cancelled out. Okay, so what will remain is, okay, so the derivation are simple. There is no complex derivations. Okay, so in this frame, of course, this is 0 because delta t is 0. So you can again write this as delta t prime plus del x is equals to del x prime. Okay. Now from this equation delta t prime, you can replace it here. Okay, you can just replace it here, but it is delta t minus b by c squared delta x to the whole square. Okay, and this is again 0, so you can, and the minus will be, no, first you have to square it, so you will get this thing. Okay. Now this will be cancelled out, and you just uh, bring this factor this side into RHS, and you will get something kind of this, and take this common factor out, you will get something like, wait a second, am I missing something? Uh, oh, this should be actually x prime squared. Wait a second. Okay, you should consider here. If I take this, it's prime, this will be 0, this will be given by minus b squared delta x squared, right? Use this inverse transformation, inverse Lorentz transformation here. Otherwise, this will not be easy. Okay, so yeah, use this inverse Lorentz transformation here. Okay, so you will get like minus c squared v squared del x prime squared plus del x prime squared. Okay, now you got it, b squared minus c squared del x prime squared is equals to del x squared. So of course, yeah, you will take its root now. So this will be, wait, this will be square root of 1 minus b squared plus c squared and the del x prime. Okay, you can also write it as improper length is equals to 1 minus b squared by c squared. Okay, multiplied by proper length. This proper length is actually measured in the S prime frame, moving frame, and it should be proper length Okay, so this is called the length contraction thing because the length is contracted here when seen from an stationary frame. So we have actually derived the formulas rigorously just by, okay, let me write what we have assumed in this. Our functions were simply constancy of the speed of light, that is del x times that is space-time invariance, okay, and secondly uh, the simultaneity, okay, of events, that was measuring the front and the back end of this rod from S frame, that is directly equals to 0, and from this we get the length contraction. So you see, from the moving frame the clocks are actually, in the moving frame the clocks are actually running very slow because the time interval is get dilated. In moving frame the time actually runs slow as observed from the stationary frame, and the rods get contracted, the length of the rod get contracted in the S prime frame when seen from the S frame, when seen from the uh, stationary frame. Okay, so these are the weird concepts of spatial theory of relativity, and we can now just quickly come to our space-time diagrams. Okay, and this is an interesting thing, space-time diagrams. So we can now see the light one thing. Okay, so wait a second. So we actually, space-time diagrams are actually drawn as t versus x. Okay, t versus x graphs, or say ctx, ct versus. Okay, now I will take this ct as an axis versus x graph. Okay, so just take this axis, y-axis. You can suppose this y-axis as ct axis. This is time axis, and this is my space axis. You can take it as x axis, or say you just take it like whole space as r vector or r. Okay, it is representing the time and it is representing the space. Okay, so you can consider this as all of the three-dimensional space here. Okay, this is called the hypersurface in like official words. So, and there is a single point in this graph. The single point represents an event. Okay, it represents an event. So I should write an event is a single point in this graph in CT versus versus X, or say R space graph. Okay. Now a world line is the sequence of events swept out by an event or a point as it moves to space and time. Okay, a world line is a sequence of events, is a sequence of events or sequence of points or a collection of points, okay, or a trajectory that is traveled by this point, particular event. Okay, event is just a point in this graph. Okay, you can call that event as point or point as event, doesn't matter. You can just say a world line is a sequence of those events, or say a trajectory traveled by that particular point, that is also called event, as it moves through the space and time. Okay, say this is the I, I get this. Okay, this is my world line. Okay, we usually do not denote it by arrow because you can already see this from the time dimension, that the time will proceed from like 0 to upward direction. So okay, obviously my object will go in this direction. Okay, so it has some constant v, constant positive v. Okay, so any particle which is traveling with a constant v, its world line will be given by this straight line. Okay, it is never ending straight line. Or say if the particle stops somewhere, it will, what will happen for a particle if it is stops somewhere, so it is here, then the world line will look like this because it is moving along the time dimension, of course. Okay, it will always be moving in this space-time graph. Similarly, if it is moving with negative velocity, it will be like this. Okay, this thing, this angle. Now, the slope depends on its velocity. Okay, in the in a frame. Okay. Now, what is a world sheet? A world sheet. Okay, then just remark these important words. What is a world line? What is a slope here? What is an event? What is world sheet? World sheet is the set of events, okay, swept out by an extended set of events, or says set of points as they move through the space and time. Okay, as they move through space and time. Okay, extended set of events. That is, it can be represented as, like, suppose this is my set of events on. Uh, Let me take something else. This is my rectangle. Suppose this is my set of events here on the R space. Okay, so what will it, how will it transverse if it is going in the negative x direction, negative directions? Okay, this whole thing should propagate like this. Okay, at every segment, this whole thing. So this is my world sheet. Okay, covered by an extended object. This is my extended. extended object of some length. Okay, moving at negative constant velocity. Okay. Now let's see let's see how how ct prime and ct prime and x prime axis. Okay, this is separate section. Okay, let's see how ct prime and x prime axis look in this c versus x graph. Okay, because let's see how, like, we can see the s prime frame in the s frame itself. Okay, so yeah, so from Lorentz transformations we know this is gamma ct prime minus beta x, right? And x prime is equals to gamma x minus beta ct. So that's now you understand why I'm taking ct prime and ct, because I want to consider ct as a coordinate. Okay, and again, yes, that was the another reason that ct is of dimension length, so it will look more symmetric, and I will take this as coordinate axis. So the graphs will be drawn with respect to this ct, not only t. Okay, so it just simplifies our things. So t prime axis, how do you draw t prime axis? How do you draw t prime axis? It is the set of events, okay, for which my x prime will be 0. Okay, you know this already, that what is my y axis, what is my, how do I draw my y axis? At my y axis, my x is 0 always, and how I draw my x axis, right? Y should be 0 at x axis. So similarly I am taking this thing. Okay, so for to draw my t prime axis, I need to consider x prime equals to 0. Okay, so if you have any question you can ask. So yeah, so what will be my x prime, what will happen if I put this x prime is 0? So this will lead to x minus bt c is beta ct. Okay, and this will imply this will be equals to this, and this will imply t equals to ct equals to 1 by beta into x. Okay, this is the graph of t prime axis. Okay, this is the world line of t prime axis in the tx graph. Okay, so you just compare it with your this equation of line. Okay, where this is your slope and this is your intercept. Okay, so your slope is actually 1 upon beta, which is can also be written as tan theta. Okay, so from here you just can calculate, like tan theta is equals to tan inverse beta. This is your actual angle. Okay, so how would, and the intercept is of course 0. So how would this axis look like? Okay, let's derive for x prime axis, then we will draw it. Okay. or x prime axis, my what will should be 0, what should be t prime should be 0. So what will happen, t prime will be 0. You can write it this also. So this will be gamma c t minus beta, okay, x equals to 0. So this will be ct equals to beta x. Okay, this is my trajectory or say word line of x prime axis in the tx graph. So my slope is slope and equals to beta equals to tan theta. This will imply theta will be equals to tan inverse beta. Okay, so the angles will look like in this graph. This is my, suppose let's take it x-axis. This is my ct axis. Okay, so these graphs will look like this. Okay. So for x prime axis, my angle should be tan inverse beta. Okay, and this angle, this is my x prime axis, and this angle will be tan inverse 1 minus beta ct prime axis. Okay, so this is my s prime frame axis, and this is my s frame axis. That's how we draw graphs. Okay, so let's check graphically what happens. Wait a second, let me present something else. Desmos. Okay, I think you are seeing this Desmos thing. Okay, now you just see, let's consider y as our ct, okay, and beta as v by c. Okay, we have defined this earlier. Now y is equals to beta x. This is same as what we have wrote for our x-axis. Okay, that ct should be equals to beta x. You remember we have wrote it for x prime axis, ct equals to beta x. Okay, and the second one, blue one, let's make it green. Uh, this is for t prime axis. This one is from t prime axis. You can check what we have derived. Okay, this is ct is equals to 1 by beta into x. Okay, this is for t prime axis, this is from x prime axis, and you can just check that this axis, that is s prime, in s prime frame, the axis that is x prime axis will be looking like this, and t prime axis will be looking like this. Okay, and you can check that when beta equals to 0, okay, when there is no velocity, these two frames do coincide with our initial frame, that is s prime s frame. So of course that means if the velocity is 0, the s prime frame is not moving at all with respect to s frame. Okay, so of course the axis should uh, coincide, and when you increase this beta, okay, you will see that it will coincide like this, and this is the trajectory or say the world line of light itself. Okay, we will see this trajectory of light, how does it arrive. But you can see when beta is 1, why will beta when the beta is 1, the velocity of an object is equal to the c. Okay, so this is a word line of any object that is traveling with the speed of light. Okay, and so actually the x prime axis and t prime axis do coincide okay, do coincide in the tx graph, ctx graph of S frame. You can just see that how is my axis of S prime frame evolving as I increase beta. So let's come to something else. Okay, just wait, I have to cover something. You can of course check yourself, check yourself how CT and how CT and X axis will look in CTX CTX prime versus X graph, X prime graph. You can check that how will my S frame look in the S prime frame. Okay, how will the axis of S frame will be represented in the X prime frame. Okay, so to remove the prime confusion, we just remove this. Yeah, that's better. And you will see that it will look like this. This is my prime coordinates. Okay, you will see looking like this. This is my city. This is my x axis. Okay, this will actually be tan inverse minus of beta. This is actually tan inverse minus of beta. Okay, do it yourself. Now we need to do something that is very much required in the HDL. Okay, to actually explain the causality. Let's take again the spacetime interval we defined before. And what it is, we have defined it like this. Delta S squared should be equals to minus C squared. Again, this is we are defining in general. Okay. This is a small interval, or say any interval, not even small. This is delta, that's why it can be anything. Delta x squared plus delta y squared plus delta z squared. This is my interval equation. This is an important thing, important equation. Now see, for light, what will happen? Or say, not for light. We will consider general cases, not just for light. So, case 1 is when del x squared is 0. Okay, what will happen? Just let's quickly check that this will imply my delta t squared is equals to del x squared plus del y squared plus del x z squared. Let's consider that, let's define it as like del r squared. Okay, let's define this magnitude as this. You will see, what you will see, that yeah, wait, So from here you can write del r squared equals to del t squared, and you can just define it as okay, it will be positive, not this. So c is equals to del r by del t. We define this as the velocity of a particle. Okay, velocity of any particle, any particle is v. Okay, so from this you get that the velocity of any particle is actually is speed of speed of light, or say the c is constant. Okay, in this case, so for such cases, such case, okay, any object, any object following del x squared equals to 0, okay, its speed will be like constant c. Okay, you can call it if you are taking the photons, suppose if you are taking, if you are only talking about light, then its speed will be like this c, that you know it is equivalent to 3 into 10 to the power 8 meter per second. Okay, and such events, okay, that this del is actually the interval is between the two events. Okay, if you are taking a photon, this interval is about like photon traveling from one place to another. You can call it an event 1, event 2. Okay, so that's why you are just describing this in the interval form. So you can consider such that any two events following events following delta x squared equals to 0. Okay, this is equals to this or could be light like separated. Or light like separated. This is an important term. You just have to remember it. Okay. So you just see that for okay. One more thing, you can just check that your V by C is equals to 1 from here. Okay, from this equation, from this first equation, okay, V by C is equals to 1. This implies beta equals to 1, or say tan theta is equals to 1, sorry, tan theta, I mean, yeah, the slope is 1, so the theta will be equals to 45 degree. Okay. Now, so let's draw it. Okay. This is my R space, considering all of the 3D hypersurface, 3D space. in just one dimension. Okay, sorry, there are three dimensions in this one axis. Okay, and this is ct. So how will the trajectory of a photon look like, or light? This is the device I'm using. So let me just start from here. Just go in negative x direction, then negative y direction. You can just extend it in the negative time direction. So you see, this is a hypersurface. You can say this is my surface of R. And make it a surface. Okay. Let's make surface. This is my surface. It's not visible. This is surface. Okay, this is space surface. You're considering all of the three dimensions in the surface, then this trajectory will look like the proton trajectories will look like. Okay. Like a cone. Okay. It will appear like a cone. And this is called the light cone. It's called a light cone. You just see. Okay, this is my negative time dimension, and any object that is here will reach here, or in the positive time dimension. So this is called light cone. Okay, and at this cone ds squared is 0, and the speed is c, okay, of any object, and this angle is 45 degrees, right? So this is what I have shown in the initial thing. This is the actual cone. This is your future light cone. This is your past light cone. Okay, this is the hypersurface of the present, or okay, you consider this origin as your present time. Okay, and this is the space hypersurface of space coordinates, and this is the cone, light cone. Okay, let's quickly go for other cases, and it will take only 5 minutes now. Like case 2, consider this is greater than this, so this will imply, let's just take the simplest thing, c squared dt prime squared plus dx prime squared should be greater than 0. Okay, not in the prime. Okay, minus plus del, this is delta, this is delta. Delta r squared should be greater than 0. This will imply that minus c squared delta t squared should be greater than minus delta r squared. This will imply that c delta is this will imply that c is actually, yeah, del r by Del t, you can define it as c less than greater than b. Sorry, less than b. Okay. When an object travels with speeds greater than speed of light, this is the interval should be greater than c. Okay. Speeds of objects are greater than speed of light. Okay. Now find the angle. Here the beta is actually v by c, of course, and from here you can see that v by c is greater than this. Okay. So you can like write this one as tan inverse 45 degree. Okay, and you can just write like as tan inverse beta or something. Wait, let's not define things like this. We have already have an equation. And how should I write this? Yeah, actually beta is, you can check it like this. So you can define your theta as 1 by beta. Okay, so see, theta should actually be, from this equality you will get, should actually be greater less than 45. Just find this. Okay, I'm not getting it right now. And for we have again a second case, a third case, that is del s squared should be less than 0. Okay, we just find it out, and this should lead us to like the opposite of this. Okay, that is c should be greater than b. This should imply this, and the theta should be greater than, the theta should be greater than 45 degrees from the x-axis, or say the r hypersurface. Okay, so you can see that in this cone, this is the cone, and this is suppose r, and this is ct time axis. Okay, so this is this cone, this particular cone, inside of it is time-like, separated, or time-like region, you can say, where your ds square should be less than equals less than 0. Okay, and here the speed of any object is should be less than c. So any object traveling with speeds less than c will always be inside in this cone, and this region, this outside region. Okay, let me, so this outside region, okay, so this outside region is space-like region. Okay. Here the ds square should be greater than 0, and in this case v will be greater than 0. So it seems like, not seems like, it is like usual particles do, usual, say, physical particles with masses do uh, travel or have world lines in time-like region only. Okay, so all the particles here, okay, all the matter particles are described by this region, okay, and we do not actually have this space-like particles yet. But we can define theoretically that particles that travel with greater than speed of light can be described in this region, okay, space-like region. But for our normal particles that we actually see in the experiments or in our nature do actually behave uh, in like this time, behave or say travel in this time like region only. Okay, so one thing also, ordering is invariant in time like region. Okay, so this means if any event A is happening in S frame, then it will be also same ordered in prime frame. Okay, this is causality is followed. Causality is followed. I will talk in the next class in time like region. Okay, but in space like region, ordering is not followed. It may happen like if it is this in S frame, then that can imply that in S prime frame this is greater than this. Okay, so causality is actually, what is causality? Causality, causality means that a cause must always happen, okay, before its effect. Okay, you know what is cause or effect, right? If I have a gun, like, okay, if I have a gun and it shoots a bullet, okay, and it just hits a person, okay, it hits a person, then this is my cause because I shoot a gun, and this is my effect. Okay, so in time like region, this will always be followed, that cause will always be the cause of effect actually. All cause will happen before the effect. Okay, but only in time like regions. But in space like regions, this can be reversed. This can be reversed in space like regions. Like that effect is like he died, suppose. Okay, and this is I shoot, I shot a gun, shot him, or bullet just fired, firing of bullet, not shooting, firing of bullet is my cause. He died because I fired him through a bullet. But in space-like regions, it may happen that he died and then I fired a bullet. So the effect can happen before cause here in the space-like regions. But it doesn't happen in our nature because usual particles, okay, usual particles do only follow, only travel with speeds less than speed of light. Okay, this is the thing, that usual particles in our nature do travel at speeds always less than speed of light. Okay, so let's end it here. But if a particle is traveling greater than the speed of light, okay, so he will be covering a space-like region, and this can happen. The causality rule can be broken down. Okay, and some examples are like anyons, and these are hypothetical particles. There are many hypothetical particles not found yet. Okay, so let's end it here. Okay, we'll talk about it more. Thank you. So, any question if you have, just tell me.